Okay, so now that we've gone over proper rotation axes, CN, and also different types of mirror planes, we can define what's called an improper rotation axis. This is called SN. And so all this is you're going to do a CN, and then you're going to, after that, do a sigma H, a horizontal reflection. And so we can write it this way, CN X sigma H. It just means do a CN, then do a sigma H, okay? So you can see that here. First, this is a molecule, maybe it's methane, some tetrahedral molecule, and you did a C4. So A kind of went 90 degrees from here to there. You can see this is not symmetric at this point, right? I mean, this A is in the front on the right here, and there's nothing front right here. There's nothing there. So this is not symmetric at this point. But then you do the mirror plane afterwards, the horizontal mirror plane. It's horizontal to the perpendicular axis, right? And then that brought this A that was over here on the right to the left. And lo and behold, look, that's where C was, also a green atom. And so you can do that, track all the points here. They all go into one another. So this molecule has an S4. We just did an S4. We did a 90-degree rotation across the principal rotational axis, and then we followed that up by a sigma H, a horizontal mirror plane. That gave us a symmetric response, okay? So there it is again, that's your S4 with the horizontal mirror plane shown. Here's an S6 example in staggered ethane. And so how you can visualize this, now I'm gonna track one atom, but kind of all in one go. So I'm gonna rotate it 60 degrees. That's gonna bring it in between these two hydrogens, but then I'm gonna flip it, right? Because I'm doing a sigma H, and so that's gonna flip it down. So you can see that tracks down. This one would go back between these two and then flip down, okay? And so that's how all these work. Let's just visualize that on Otterbarn's website. Again, using cyclobutane, that has an S4. And so if we hit the check mark there, it's showing you there's the S4 axis. That's really a C4 axis. And then after that, it's going to be a sigma H. So if we play this, you can watch this go where we're doing a 90 degrees rotation. There's the C4. And now we're going to do a flip. And there's the flip. Okay, so you can see this molecule, it had a C4 there, but it also has an S4. Some molecules only have improper rotation axis. You might be thinking, well, isn't this sort of cheating some way? Why don't we just keep it, you know, CN and sigma H? And the reason is because, and why don't we just talk about those two separately? Isn't this cheating because we're just combining two symmetry elements? The reason is because some molecules only have, it turns out, improper rotation and no proper rotation. So you need that flip to get it. So mathematically, this is actually a distinct rotation. It's a distinct symmetry element. And this is just a property of three-dimensional space and symmetry of three-dimensional space, okay, is that these rotational axes are mathematically unique. Very last one is everybody's favorite because it's the easiest. This is the identity symmetry element. And this is the symmetry of something that is of itself, okay? This is given E. This is just do nothing. So everything has identity, everything has E. This seems totally useless, but turns out very mathematically useful. And for all the problems we do, we have to consider the identity. Some molecules only have E, okay? They're shown here. So example would be consider a tetrahedral center, so like a methane analog that is substituted by 4 different atoms, right? This has no other symmetry element than E, than itself, okay? So that's all of the different symmetry elements that there are in three-dimensional space, and all the symmetry elements, again, point symmetries. We're not dealing with space symmetries in this course. All the different point symmetries that exist in three-dimensional space and that are applicable for all the molecules we'll be dealing with.